Thank you very much. I want to start this talk with preventive thanks. If something's going wrong with the demonstration, I've already thanked everybody. So first of all, I thank the program committee that have selected my talk, so they gave me the honor, responsibility to give this talk. Preventive information. If you are looking for more information about the projects, you can shoot at me. I mean, with your photo cameras, with your cameras. The largest one is the wiki site. The smallest one is my email address. Okay, and if you find me outside, so I need to wear something more than my shirt, the same QR codes are here, okay? So, in the beginning, network was made by hosts. So the addressable entities were these interfaces. This is quite new for me. It's a 10 megabytes with the coaxial socket. When I started dealing with networking, we had the thick cables and the vampire top drop cables and so on. Anyway, when you are looking for something, you type a fully qualified name, and there is a domain name server that translates into address. And what do you name with that number, with that IP address? One of these. So the situation is this. You have an IP address. This yellow box is a piece of hardware. You name the interfaces. There is a table of, there is the server side, client side is quite similar, but there is a table of listening sockets. And you reach your server because there is a mapping between the socket number and your daemon. Now I have to explain this picture here. It's funny that it gives continuity to the session because the previous talk was about internet telephony. But I decided to insert that icon on Friday night. I was in a very crowded place named Delirium Cafe, and I was beer storming. Did I say brainstorming? Okay. And I was looking for a way to describe the difference between the current internet and the internet of threads. And it came out that the telephony system is quite a good example. Long time ago, we had fixed line, so that we had white papers, and we were able to find people because we looked for people into the white pages. We dialed the number, but in the reality, we didn't find out people. We found out houses, because the phone line addresses houses, not people. Okay? So it's exactly the same. You're addressing the house of processes. This is yesterday. It has been a good thing. It was good. The evening and the morning were. Second day, we are developers, so we are creators. We can use biblical words. Today, virtual machines have IP addresses. So we are addressing virtual interfaces. We are very young developers. We are addressing virtual interfaces of virtual machines. We have just virtualized the entire box, but we are keeping the old concepts, virtualizing old concepts. Other example, if you are running high availability servers, you give a number of different IP addresses to the same interface, because you want to be free to move the services by moving the address. It's like in the metaphor to have a number of different lines, like in the Oval Office at the White House. There is a red telephone, because you know who is calling at that telephone. But you're always addressing the Oval Office, not directly the president. What's the difference? What has happened today? We have portables. So we are addressing people, not houses. And so we don't need white papers to address houses. And Internet of Threads, so the Internet of Threads is this. Instead of giving addresses to interface, we embed the networking. We can embed. We are not forced to. If we can have, we have the opportunity to embed the networking support into processes. Why? I've listed here a number of I think hard problems. For example, if you want to provide a specific address to a specific user, you can create you can give one more address to your interface, and then you have to play with IP tables to divert the traffic to that process and so on. You can, but it's not natural. If you want to provide different quality of service, different routing for different processes, if you want to run in several servers on the same interface plus port, a port is like a PABX. So you dial the number and then you have the extension. If you decide that the extension number 1 is for the boss, like we decide that the socket number 80 is for web, it's okay, provided you don't have 2 bosses. Otherwise, you don't know why to assign the number 1 to one instead of the other. So they start fighting. Or using VPNs, or you can read the slide. Migrate processes is another hard problem. Why? Because we have IPv6, so we have plenty of addresses. So doing this in IPv4 can be hard, because we have to count addresses one by one because they are scarce. But in IPv6 we can use it, and given we have so many addresses, we can return back to Chalk and Blackboards to redesign a new internet. And we must find a way we must find a reason to think to IPv8 or IPv4, because we are developers. Only people who are thinking to ancient Roman, ancient thing, use X to name 10. Okay, I've heard about an operating system, but okay. Okay. Have you heard about the Internet of Things? Internet of Threads. So the Internet of Threads is the software counterpart of the Internet of Things. So Arduino is a wonderful piece of hardware, but it's too limited. So you have to reprogram it to flash it again to have the Arduino do another job. And so in some sense it's special purpose. In the same way the rabbit rabbit or rubbish, rabbit, are quite special purpose. They are just toys, and as soon as you wanted to change the service, you wanted to change something, you had to throw them away and buy a new version. It was what the hardware vendors want. Now we are going to have more powerful hardware like the Raspberry Pi. So we can do what we are doing with the Internet of Things in terms of software. So we have Internet of Software Things. I mean, Internet of Threads. Why? You say, we have Linux containers. You can give addresses by Linux containers. That's true. But it's another story. Linux containers are for system administrators to provide services to users. Internet of Threads is for users. So users should be able to define their IP address, to reroute their network traffic without the need of root access, of being sysadmin of their machine. Obviously, I've not rewritten Firefox yet, but I envision that in the future there can be the way to choose the network as we choose the printer now. So you can have a menu saying, oh, I want to see the network through that VPN or the other, because it's up to the user to decide IP addresses and routing. And because it's a natural way to do networks. Have you ever tried to tie interfaces together? You need some kind of ropes, wires, or threads. So a network, even in the common behavior, in the common idea, is made up of something that can be tied together, like threads. These are the examples that hopefully I will show you today. Browser providing different perspectives on the network. So I started as a browser, and I moved the browser in different countries without even restarting the browser. And I repeat, everything as a user, no root access. Virtual appliances, so that's the server part. It's these are servers with the networking attached. So you can migrate servers just by killing a process on one machine and starting the process on the other. No configuration of the interface, no rerouting, nothing of what you did yesterday. Or this is the new point. I'm presenting this for the first time. One-time IP address. You know, one-time password. One-time IP address. Sometimes I get worried at home because somebody tried to enter my system, tried to provide to put in place brute force attack, or maybe on SSH, maybe on my VoIP system. SSH, VoIP are my own services, so I don't want the other to. I want to be able to access my service, but they are just for me. So I can use the same idea of one-time password, and I can change the address. In the example, I will change it every 64 seconds, so that even if somebody is looking at the traffic on the network, is listening to the network, is using Wireshark, and gets some addresses, they are useless in 64 seconds. So, before having a look at the demos, what's behind the stage? we need a number of technologies, but luckily we have developed them. The first one is the network. So if you have processes which are network nodes, it's hard to connect one piece of software, like a process, to an hardware switch. So you need a software switch that is able to connect the software processes. And VDE, Virtual Distributed Ethernet, provides this kind of switch. So the network enters into the logical part of the machine, so the processes can get connected to the virtual switches. We can use all the standard stuff, all the standard tools we use on physical networks for processes. For example, we can ask processes to acquire their address by IPv6 auto-configuration or by DHCP, like usual. You can set up hybrid networks, so networks that are partly real, partly virtual. And from the outside, you are not able to distinguish between real nodes and virtual nodes, and threads or hosts. Virtual Square, this, is a community that has created all these tools. The other tools we are using, let me skip these are just advertisement. Oh, if you read the interview, I have a kind of childhood trauma about building sets. I had incompatible built-in sets. So that's why today I'm creating ways to integrate different virtualities. Okay, that's just advertising. Oh, we're doing it better. We have virtual distributed Ethernet. Then we need the stack to embed the networking into the threads. And this is our stack. LWPv6 is a stack, is an entire stack implemented as a library. It is IPv4, IPv6. It's hybrid. It means that there is just a forwarding engine. And we have VOS, which is a partial virtual machine support. It means that you have a virtual machine that can virtualize just file system, just networking, and so on. I think it's better to have a look of all this tool by looking them at work. So let's start with the first demo. I need your imagination. As you can see, as you will see, I don't like icons. So you will see a lot of command line commands, command line interface. So you have to imagine what is happening behind. So first example. So let us have a look at the example. I start a browser. The browser is connected to a switch, and the browser is Firefox, but it's using our LWPv6 stack because it's running into a virtual machine. It is connected to a VDE switch, and I use a VDE slurp on the other end. I mean, that's a process that is a standard process for the hosting machine, and it's a router for the virtual network. We provide this as a dynamic linked executable, but also as a static link executable. So you can just bring this executable, copy in the machine that you want to use as your default route, and as a user, you will route all your traffic to that machine. Okay. Let's start. This window on the left is just a list of commands. I start the slurp VDE locally. I start the virtual machine here. I hope it's not too small, the font, because can you read from the back? Yes, no? Yeah. Raise your hand, yes. Raise your hand, no. My God. Okay, I'll try to have the font bigger just on the terminals where I am showing something very interesting. Because otherwise all the windows can't fit to the screen. So here there is the slurpvd. Now this is the virtual machine. This is an empty virtual machine. Okay. Now I say to this virtual machine, virtualized networking and file system. So now I have my real, because I'm in the virtual machine. Now, I want to check, just to check if I'm out of the network, of the real network. So that's matter. That matters for just a minute. I bring down and up the wireless. It's a problem with the wireless. Okay, tell me. This is not related in any way with the. Okay. No. I think we have a problem on the wireless net. Are you using the wireless net in the room? Is it working for you? Oh, no. Who says no? Because I have received an IP address, but okay, tell me. Cross your fingers, please, everybody. I tried this before. Okay, it's up, but it's okay. It's up. It's up. Okay. Let's go on. So we were at this point. Now I start the virtual networking. I bring up the interface. As you can see, I have different interfaces now, because now the networking is virtual, not real. So I virtualized the file system just because, unfortunately, the information about the domain name server is in a file. So I have to virtualize the etc resolve.conf file. That's very nice for having partial virtual machines, because I can virtualize just the file. I say that file is virtual. So I can bring the network up. Okay, I've got an address. And now I can start the Firefox. And hopefully, new, okay. There is a bug I'm looking for, but the second time it's the charm. Okay. So, cross your fingers. Is the network working? Let us see if the real network is still working. Okay, it's working. Oh. The nice part of the demo is that okay, let us retry it from the scratch. Maybe large fonts have put the system in trouble. Okay, there's okay, and now Firefox new. Okay, we are in Belgium, and you know we are here. But now I try to connect the cable from my VD switch to Sleep VD in Bologna. Hopefully. Please, please, please. Okay, University of Bologna. But we can move now. Now I like the game, so never try too hard. Lucky. Okay, it works. It worked once. No, okay, let us move to the second example. Okay, that's Kansas City. Okay, but we have seen this example. Let us move to the other example. I hope the networking is following me. The network be with me. Okay. So now I connected the network to Bologna. And with a VDE switch which is connected to the internet. And I started this, there's a Contiki host. Do you know Contiki? How many of you have heard about Contiki? Contiki is an embedded system, is an operating system for embedded systems. Here I've created a virtual embedded system. So all the web server, the whole web server is 140K. So, but I show you this first. There is a standard browser. Okay, I'm connected to my web server, but I hope you will not try into many, but if you try, you can reach this very web server typing its IP address. Because I'm on the network, I'm on the internet, but the process is here. It's Internet of Thread, server side. There's Contiki, but I can do the same using our LWP server. I'm turning off the web server, so if you tried, okay. Otherwise, don't tell if it's not working. Control C, and the server disappears. Okay, now let me try this test. Okay, now I've started another service on 42. Okay, this is a virtual NAS. It means that a virtual web server, I think that in the future it can become a virtual NAS. So instead of having a hardware NAS network, the box you buy for your home to connect your computers, this is the virtual counterpart. So it's a web server. It works. It works. Now we can do something like this. I need to open several windows. The first one I connect to Bologna. And from Bologna I connect a switch in UK. I need the password. Okay. And now I connect it to my virtual machine in the UK. Tests, web appliance test. And now I Control-C the server here and start the server there. I reload the page, and it's already running, but I moved the server from here, from my laptop to the UK, because the server has the networking stack embedded. So I can have instead of reconfiguring the network, you can just start the process. And now, this was the demo number 2. Now, roll the drums. The most difficult one seems to be at the Circus. Okay, who am I? An elephant or? Okay. One-time IP. What's a one-time IP? You know one-time password? I explained. So you use the same mean to have your private address. The architecture I'll set up is this. I have my browser. Unfortunately, Firefox is not able to understand the URL, including passwords. So I've created a syntax. If you have the name of the host name, __ a password, that's an extended URL. We can decide in future to have a better syntax, but I want to show the idea. Firefox is not able to translate this kind of addresses. I use a DNS forwarder. So Firefox ask the query to the DNS, which is the DNS forwarder. The DNS forwarder is able to parse the new syntax. It takes the host name and asks for an IP address, IPv6 address, to the real DNS. It gets the answer and compute the actual address by combining 3 things: the base address, the password, and the current time. It computes a hash, and the hash is the lower 64 bits part of the address. On the other side, I have a switch and I have a server which is able to jump from an address to the other. On the reality, IP addresses last for 128 seconds because the validity of an address begins 32 seconds in advance and terminates 32 seconds late. So that if there are inconsistency drifts in the clocks, we can manage them. Even in the real internet, 32 seconds is a geological era if you have NTP. And the other point is TCP sometimes has a long-lasting connection. If you have an SSH connection, it can stay on for hours. That address remains valid just for that connection, and the listening port is switched off, gets switched off. So no more connection to that address are allowed. But I'm not giving just addresses. I'm really starting and stopping entire stacks. So I start a stack, I configure the virtual interface, the addresses, and after 128 seconds, I switch off the stack. Let us try. Okay, let us close all the other stuff and return back to the beginning. So, OK, this can stand. I'm not virtualizing anything yet, so let me see if we have new problem with the network. No, the network is OK. So why I'm not resolving this IP address? This is not virtualization. This is real networking. It seems we are in trouble with DNS. I have trouble with the DNS here of FOSDEM because it's not, I'll try to bring the networking down and up again to see if something is working better. OK, at least it seems that how can I come out of this? The DNS works for you? Yeah, but I need an open DNS server. You have one? Sorry? .8.8. OK. So, thanks a lot, guys. When at 888, there is a quote. OK, thanks a lot. OK, the database address of that we will use. Now, the real DNS is not able to parse these addresses, obviously. So we can virtualize. We can virtualize a process. We can further modify it as a user, etc.result.conf, and move as a user the name server to be one private address. And then I start. I need more windows. No, not in that sense. I can start my DNS forwarder, which is here. Now I forward it to 8888. OK. Now, from within this virtual machine, the old address is mapped to a normal address. But the new address with password has computed, OK, wonderful, has computed the current address. So if I return back in 64 seconds, let us say, OK, in a while it changes. But we can start a web server here having a OK, I can use this. Tests, web test. Now I start this here. As you can see, I've changed the address. But now I can start my Firefox. OK. And I can, OK, this is my website. If I reload the page for a while, I can navigate it. I can enter the file. I can reload the page. Reload, reload, reload. Actually, this is online. So if you are able to transcript the long IPv6 address, you can reach the very same web server. Don't try too many, otherwise in a while. OK, let's change the address, but we are still online. So this is one-time IP. You can have your server changing dynamically the address, but if you are the legitimate user, you can follow the change of the address of your server. OK? You can do this on a real network. You can do this on private network. For example, we have public VDE switches. So you can connect to this public switch, and you can create a worldwide local area network. Because it is worldwide, but it's not connected to the internet. So I give you a suggestion. Imagine if you write a BitTorrent tracker that is able to change its address from one place to another, and it's inside a virtual LAN. Unlegitimate users or people who don't want you to freely express your opinion, for them it's hard to track your service down. OK? So, a word about security. We have the principle of least privilege. Each process must be given no more privilege than necessary to do its job. I don't know if it's always considered in the right way. For example, we are overusing the sysadmin capabilities. I don't know. It happens to me. It happened to me, but I think it happened to all the system administrators to type rm a file, and as soon as you entered the enter key, have pushed the enter key, you start wondering, but which one the directory was? OK? So being root too long is dangerous by itself. So putting the services outside giving the user the freedom to create their services by themselves, it means to have a more solid system. We will discuss in the afternoon in the virtualization and the cloud dev room about this topic. If you have a lot of services in the kernel, you have a huge kernel with a lot of services, and there is a famous theorem that says the larger is the code, the most probable is to have bugs. And this relation is more than linear. So this was what Andy Tannenbaum said to Linus Torvalds. Microkernels are better. So if we are able to put services outside the kernel, we can have a more flexible system. My point, and this is the point I will discuss in the afternoon, is that we can have milli-kernels. So neither kernel, not microkernel. People from NetBSD are talking about any kernel. It's quite the same concept. So a kernel that can be configured to be a monolithic kernel, a microkernel, or monolithic for some services, a microkernel for others, up to the sysadmin needs. Okay. So one word about performance. Okay. It is heavier to have stacks outside the kernel. So if you do benchmarking, for sure the kernel stack wins. But do you remember the first portable phones? They were huge. During the time, if the service is useful, we provide better support. That's my point. We can't think just to performance. We have to open our minds and think to what's useful, and then we can find out the right support to provide performance. VDE, there is a kernel implementation of VDE, and it's quite fast. We have not yet written or found a way to use a stack at kernel level. Network stacks are ordinary business for users. Inter-process communication in the cloud is done by processes. So this is the way to do inter-process communication if you are thinking in a cloud way. That's all. Thank you. There are questions? Please.
So you're effectively frequency hopping into the same thing with the host part of the IPv6 address. Is that 64 bits enough to add real security?
There are 2 points about this. The question is, is 64 bits enough for security? In a probabilistic sense, it's 1/2 to the 64th the probability you have to get the right address. And even if the entire internet today, which is mapped on 32 bits, so the maximum number of hosts you can have is 2 to the 32, is on one single local area network, the probability to have collision is less than 1/2 to the 31, because you have 2 times the number of space, because each one can collide with another. So it's quite rare, 1/4 billions, if the entire internet is on one LAN. I think it's enough. We're working on that. I know there are troubles for the number of nodes. but we have also technologies. They're not inside because we can't cope with the standard minimum spanning tree. But there are software-defined networks. There is the 802.1AQ protocol that can be used. We are envisioning ways to take care of that problem too. Last question.
How do you compare with the network namespace, which is a feature already implemented in the Linux?
That was the slide about containers. Network namespaces were for system administrators more than users. So it's not having the network stack embedded. Another nice point to have the network stack embedded is that if you want to migrate a process, imagine that you have a real working freezer to stop a process here and restart there, keeping the state. If your networking state is in the kernel, you have to pick up all the information about your connections and save it and move it. Instead, if it's inside the process, it's the natural way to do it. Okay? Thank you a lot. And sorry for the problems in the demo, but I got the risk.